Back in 1828, long before the phenomenon of why you have electricity flowing through conductors was even discovered at a microscopic level, it was G.S. Ohm, a German physicist and a mathematician, who discovered a unique relationship between the potential difference applied between the ends of a conductor and its relationship with the current that flows between the ends of the conductor. He discovered that it was pretty much analogous to the temperature difference between two ends of a metal and the speed at which heat gets transferred from one end to the other end. The more the temperature difference between two ends of a metal, the speed with which heat gets transferred to the other end is also quicker. So he thought that a similar analogy might exist between potential difference or the voltage that's applied between the ends of a conductor and the flow of current between the two ends. And with experiments, he discovered that there is a linear relationship, that's the two quantities are directly proportional to each other. To remove the proportionality constant, he introduced a constant of proportionality called R. R is described as resistance, and it's given by the symbol and named in his honor as Ohm. So R equates to the ratio of voltage by current. This relationship V is equal to I into R is famous as the Ohm's law. Now, this factor resistance that is introduced by G.S. Ohm is dependent on two factors. One, it's dependent on the nature of material, and two, it's dependent on the dimensions of the material that is in question. So let's do a couple of demonstrations on how R is dependent on dimensions. So let's take a cuboidal piece of metallic conductor which is of length, let's say L, and it has an area of cross section capital A, and we apply a voltage V across it, and let's assume that the presence of this voltage causes current I to flow in this piece of conductor. Suppose I decide to increase the length and make it exactly double. So what I do is I take two such conductors. Each of length L, and then join them end to end. So each of length L and L, and the voltage applied across the end of each of them is V and V. and the electricity that's flowing is I. Area of cross section happens to be the same, which is A. What do you think happens to the resistance of this combination? So let's say resistance of the combination is the total net voltage. So voltage across this part is V, across this part is V. So it's V plus V, which is the total voltage, divided by the current. The current that's flowing is still the same, which is I. So you get 2V by I. But initially we said R is equal to V by I. The resistance across one such piece is given by the ratio of V by I. So this becomes 2R. So what do you see here? We see that as length increases, resistance too increases. Length became 2L, resistance of the combination now became 2R. So you see, resistance is directly proportional to the length of the conductor. For the second scenario, I am taking the single piece of conductor which is of length L, and I am cutting it in half along its length. So I get two pieces which are of cross-sectional area A by 2 and A by 2. The length of both these pieces is still L. The voltage that's applied across these pieces is still V, and the current that's flowing, which was originally I, now it has been split into half. So the current that's flowing here is I by 2 and the current that's flowing here is I by 2. Now what do you think is the combined or the resistance of one of these blocks? What is the resistance of one of these blocks? So let me call it as resistance of one block. That's again given by the ratio of V by I. V is still the same, which is voltage that's applied across the entire length, but current has now become half of original. So effectively we are seeing that it becomes 2V by I, which means R1 is 2R. So again you see that resistance has doubled. When the area of cross section was halved or made half of what it originally was, the resistance doubled, which means as area of cross section decreases, resistance increases, or in other words, resistance is inversely proportional to area of cross section. So we have arrived at two relationships, that resistance is directly proportional to the length of the conductor and resistance is inversely proportional to the area of the cross section. So if I combine both of these, I get resistance is proportional to L by A. Now to remove the proportionality constant, Ohm introduced again a proportionality constant that will represent by the Greek symbol rho. Rho is called resistivity. So rho is denoted as RA by L. Its unit is ohm meter. Now, if I go back to the original Ohm's equation, V is equal to I into R, and replace R with what I just derived here, I get V is equal to I into rho L by A. Now V is equal to I by A. I combine them, the reason for which will become clear in a moment. I by A is a concept we now call as current density, the amount of current flowing through a square unit of area. So we will represent that by a new symbol which is small j rho L, where J is equal to current density. And J is equal to I pi A. So we have arrived at this stage where we say voltage or the potential difference is equal to the current density multiplied by the resistivity and the length of the conductor. Now I can also say V is the product of the electric field multiplied by the length of the conductor. So then the equation reduces to EL is equal to J rho L. So L and L get cancelled out. So what I am left with is E is equal to J into rho. This is in vector form, because current density and electric field are both vectorial quantities. Now, the reciprocal of resistivity is something we call as conductivity. The reciprocal of resistivity is something we call as conductivity, and it's represented by the Greek symbol sigma. So if I put this over here, then I get the new equation J is equal to sigma E, which is one of the forms of Ohm's law.